Hi Year 12, I'm going to take you through question 1 of the AQA Arrhenius past paper questions. Question 1 is reasonably straightforward and I should do separate videos for questions 2 and question 3. So, question 1a, you need to calculate a value for the rate constant, so that's K, at this temperature and give its units. So we're going to get, for 3 marks here, one of those is going to be for the units, one of those is going to be for the correct value, and one is probably going to be for a correct rearrangement of this. So we want to find K, so we're going to say K equals rate over the concentration of C times the concentration of D. Then we're going to plug in our values, so we're told the initial rate is this, so 3.1 times 10 to the minus 3 over, where are we, C, not raised to the power of anything, so it's just 0.48 times D is 0.23, and if you calculate that, which I did already, that should give you 0.028. Then for units, so we've got moles dm to the minus 3, s to the minus 1 over this, so we can cancel, so then we've got 1 over this, so we're going to get moles to the minus 1, dm plus 3, and then S1, so that's going to be our units. Okay, question B, what have we got here? So we have been told an equation that relates the rate constant K to the activation energy, EA, and the temperature is this. By this point, if you are attempting this question, or these questions, you should now be familiar with this, the logarithmic arrangement of the Arrhenius equation. So you are asked to use this equation. In fact, I think I've been through this in a previous video. Anyway, use this equation and your answer from part A. So we've calculated K there, and I imagine that there'll be error carried forward here, so if you correctly use an incorrect answer, then you should still get full marks. So use that to calculate a value in kilojoules per mole. Now once again, I've briefly tucked myself away in my daughter's room without much equipment, so I've got this rubbish pen here. I'm going to highlight that. So we need a value in kilojoules per mole. We're told for this reaction that ln A is 16.9, and we're told the gas constant, which by this point you probably know, is 8.31 joules per Kelvin per mole. So I'm going to just circle that, and I can see here that at some point I'm going to need to convert, because they want the answer in kilojoules per mole, and I'm currently working in joules per Kelvin per mole, so I'm going to need to convert my answer. I'm going to need to divide by 1,000, and they give you a value here if you couldn't do that. When you have one of these questions, FYI, where they give you a value to use if you couldn't answer the previous question, it gives you a slight point of reference for whether you are right or not. Now this is what, times 10 to the minus 2, and this is times 10 to the minus 3, but they're not wildly different answers. If you've got a massive answer, then you've got an indication there that you've gone wrong. So it gives you a little kind of pause for thought to do a common sense check. Anyway, so we need, what do we need? Activation energy, right. So there's a couple of ways that you can do this. First of all, I'm going to try and write this down in kind of sequential steps. We've got K, but we don't have ln K. So the first step is I'm going to work out ln K. So that's going to be ln times 0.028, which gives you, sorry, just refer to my answers here, minus 3.58. Okay, so now we've got ln K, and we've got ln A, and we've got R, and we've got T. However, and I should have done this when I was reading the question, it says the activation energy at 25 degrees Celsius. Well, we're working in Kelvin here, so we're going to need to convert that. So step 2, I'm going to say T equals 25 plus 273 gives you a temperature in Kelvin of 298. Okay, so next step then, we're going to rearrange this to give us EA. Now, the way that I tend to do this is kind of the way that that you would do it when you're doing the graph. So I'm going to say EA divided by RT equals ln A minus ln K, which equals, where are we? What do we say? Ln A was 16.9 minus 3.58, which gives us a value of 20.476. So this equals this. What we want is just this, okay? So we can then say this answer here multiplied by R times T is going to give us our activation energy. So R was 8.31, T we just calculated as 298. So if you multiply all of those together, you should get a value, I'm just going to put over here, EA equals, I haven't written it down. Oh, brilliant. Okay, hang on. Okay, so the value that you get is going to be large. You will need, remember, to divide that by 1,000, and that is the most common wrong answer. So 51 kilojoules per mole, or 50.7 kilojoules per mole. This is the most common wrong step, is that people do not convert into kilojoules. They forget that they were working in joules. So when you are doing one of these questions where you are calculating activation energy, I want you to ask yourself two things. One, is it positive? The answer should always be positive. Remember, this is the activation energy. It's the energy required to start a reaction. It's the energy that you've got to put in. Okay, so it needs to be positive. And the second is, does it fall in a range of 40 to 400 kilojoules per mole? That is the range typically of activation energy. If yours is way out, if it's above that or below that, you've gone wrong. Okay, so this here is quite nice because it just gives you, you know, a common sense check basically. Okay, that's it for question 1.